So thanks for the opportunity to speak about Watson, which is always fun. Watson was such an amazing and cool project, in my opinion, easily the coolest project that IBM has ever done. And I would also like to thank my strategy teammates here who contributed to the work that I'm going to present. So I thought I would start off with a short video clip from the televised match, just to refresh your memory about what was going on there. And for the viewers at home who might not be familiar with the game of Jeopardy, it gives you a little bit of a feel of how the gameplay works. So let's see that video clip.
Let's do $1 or less for 1,000.
A 15-ounce VO5 Moisture Milks conditioner from this manufacturer averages $1 online. Ken.
What is Alberto?
Alberto, yes.
Let's have also on your computer keys for 800, Alex.
It's an abbreviation for Grand Prix Auto Racing. Brad.
What is F1?
Good.
Computer keys for 1,000.
An additional section placed within the folds of a newspaper. Brad.
What is tab?
No. Ken.
What's an insert?
Insert is right.
Let's go to dialing for dialects for 600, please.
Vedic, dating back at least 4,000 years, is the earliest dialect of this classical language of India. Watson.
What is Sanskrit?
Sanskrit is correct.
So whenever we talk about Watson, we usually spend a lot of time talking about the three major challenges that Watson had to face, or really any contestant has to face, if you want to be able to do well on Jeopardy. These three challenges are, first of all, you've got to be able to come up with the right answers. And this is what the Deep QA architecture was so amazing at. Before we did Deep QA, there was no remote speculation that a machine could ever answer these kind of Jeopardy questions at the same level as human contestants. Second challenge is you also have to compute an accurate confidence, your estimate of the likelihood that your answer is going to turn out to be right. And if you're not good at estimating confidence, you'll miss a lot of opportunities, or you may be buzzing in too much and getting penalized, and that will hurt you. And the third big challenge is the challenge of raw speed. We have to do number 1 and number 2 really fast. There's only a very short window of a few seconds while the host is reading the clue for Watson to do all of its evidence analysis, all of its confidence calculations. At the end of that interval, it's got to be completely done, ready to go when the buzzer's open, just ring in as fast as it can. So these are the topics that we normally talk about. What we're going to discuss today is a little bit different. It's a fourth aspect, and maybe less mentioned, less studied aspect of doing well on Jeopardy, and this is the game strategy decisions that contestants make during the course of gameplay. These turn out to be pretty important. If you do a good job at strategy, you can boost your chances of winning quite substantially. So there are 4 different types of strategy decisions. I'll mention a little bit about each one of them. The first strategy decision is when you're in control of the board, you get to pick a clue. And actually I have audio of Watson picking a clue.
Let's finish Chicks Dig Me.
One of the more amusing clue picks. Now, you might quite reasonably ask the question, well, what difference does it make? I mean, you can just pick any clue, right? And the answer is no, and our work has shown that it's very, very important when you're picking your clues. You want to get the daily double questions ahead of the human opponents. And this is important for 2 reasons. Number 1, it gives you a good chance to boost your own position, your own score. And maybe more important, number 2, you deprive that opportunity from your opponents. So, second big decision is... So, this is the sound they play when you found the daily double, and now you've got the daily double. Now you have to decide how much do I want to risk on this daily double, potentially all the way up to your entire bankroll. The challenge for humans is humans basically have no clue how would you go about calculating something like a quote-unquote optimal wager, and they inevitably just end up winging it. They wager some smallish round number that they feel comfortable with. So maybe it's not surprising in the hindsight of our analysis, humans just are not very good at wagering daily doubles. And so this is an opportunity for the computer to shine. If we can develop a very good, precise, quantitative method for doing these calculations, which I'll show you later, then we can potentially have a big edge over the humans. So third strategy decision is the last clue of the game is Final Jeopardy. You write down your wager in secret. You try and predict what the other guys are going to wager. They write down what they're thinking, and they try to predict what you're going to wager. So this puts us in the realm of strategic reasoning or game theory. It turns out there's actually a decent body of game theory about Final Jeopardy that's available out there. I guess maybe the challenge for contestants who go on the show, most of these contestants apparently haven't studied any of this theory. And so you routinely see contestants making egregious blunders over and over again. And it's so tragic. If they had just made the right wager, they would have won, but they made a silly wager and they had to go home. It's very much a shame. So the final strategy decision is deciding how much confidence do you need to venture trying to buzz in and answer. For most of the game, you can go with kind of a default buzz threshold, and that works pretty well. Near the end of the game, it turns out you have to start dramatically varying your buzz threshold. We've discovered a whole slew of scenarios where our calculation says, Watson, don't you dare touch that buzzer. There's nothing to gain, and if you buzz in and get it wrong, it's going to hurt you. And conversely, there's the other scenario where the calculation says, go ahead, take a free shot. No matter if you have very low confidence, it's not going to cost you if you get it wrong, and it may give you a very good benefit if you luck out and get it right. So in order to go about optimizing our game strategies, we needed to build a bunch of simulation models based on lots and lots of historical data. So this is one of the cool models that we developed by downloading lots and lots of data from this website, JArchive, maintained by the fans of the show. They upload a detailed description of every event for every episode for literally thousands of episodes. So you download all that data from JArchive, and one thing you can extract from it is where do they tend to put the daily doubles. So we've got a little heat map shown over here on the right, where red indicates likely to have a daily double, blue indicates unlikely. And so this does confirm what a lot of people know from seeing the show. The daily doubles tend to be toward the bottom, the lower rows that have more difficult questions. What has not really been appreciated before is there are also column dependencies, and there are joint row-column dependencies for the way they place these daily doubles. So what Watson can do with this is very cool. Watson can use this initial distribution as a Bayesian prior, and then it can do a live update. As each clue is revealed, we can recalculate on the fly the probabilities of where the daily doubles are likely to be. So Watson has something like an omniscient knowledge of, at any given stage of the game, which square is the square that's most likely to have a daily double. And this is something that humans can't do this kind of calculation anywhere near the precision of Watson. Okay. So after a lot of experimentation and tinkering, we honed in on what appeared to be the optimal strategy for Watson as a result of lots and lots of these simulations. So it turns out it's good for Watson to place a huge emphasis of order 90% on finding the daily doubles via this Bayesian calculation that I just mentioned, and blend that with a small emphasis on keeping control of the board. So if Watson didn't find the daily double, he would have a shot of getting that answer and being able to repeat for another chance to find the daily double. That's if the daily doubles are available. If there aren't any daily doubles anymore, then the thing to do is to learn more about the categories that are remaining from the low-valued clues in that category. So bottom line, this combination of these three ingredients enable us to boost our win rate by about 4 percentage points more than if we just did a simple row-based daily double seeking, which is probably a good model for how humans seek for the daily doubles. Okay, so I have a little animation. It's going to show you side by side Watson's daily double seeking algorithm and how it hops around and picks the clues versus actual human clue selection in actual historical games. So let's see that animation side by side. So we're going to see, as Watson's focusing a lot of effort on the clues down here, and the hotspots become very hot, and that enables Watson to hone in and get the daily doubles very quickly, versus what you can see on the right, the human historical clue selection is top to bottom, and it's just nowhere near as fast as finding the daily doubles as Watson. Okay. So this is another cool model that we've developed and used very effectively. This is a stochastic process model of what tends to happen when you're playing a regular clue, meaning it's not a daily double. So it turns out that there are 7 possible outcomes of a regular clue. You could be, at the initial buzz, it could be that nobody buzzes and the clue's over. Or somebody can buzz, and if they're right, it's over. Or they could be wrong, and then you go to a rebound, and it's the same thing. Nobody buzzes, or they buzz and get it right. Or if they're wrong, you go to a second rebound. All in all, there are 7 possible outcomes. And from the data that's available on JArchive, these are the frequencies of these 7 outcomes. So based on these outcome frequencies, we're able to devise a mean rate stochastic process model for how often contestants attempt to buzz, which turns out to be in the low 60s, and a rate of getting it right when they buzz in, and that rate is in the high 80s. And we've also modeled the correlation between human opponents. Humans tend to be correlated, and both for the buzzing and for getting it right or wrong, the correlation appears to be a modest value in the realm of 0.2. So what's cool about this model is this is a model of 3 human contestants, and now we can replace one of those simulated humans by a comparable simulation model of Watson with suitably tuned parameters for buzz rate and precision. And now we can run gazillions of simulations to our heart's content of simulating the play of Watson versus 2 human opponents of known ability. And this simulation capability is very effective for us for optimizing our strategies. So here's one way we've made very good use of this model is in coming up with a very good way of calculating daily doubles. So what we do is we train a neural net to estimate Watson's probability of winning at any given stage of a Jeopardy game using millions and millions of these simulated trials that we talked about. And in this effort, we can very fortuitously make use of the work I did previously on TD Gammon, which was a neural net that was able to teach itself to play backgammon at a very high level. So TD Gammon is a neural network which would generate a sequence of positions starting from the opening positions. It would make moves for both sides, so move, 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 go all the way to the end. You find out at the end who actually won that game. And now, with that data, you can use a reinforcement learning algorithm called TD Lambda, which enable you to slightly adjust your predictions to make a slight improvement in each of those move decisions so that your next game played will be a little bit stronger than the previous game. And you keep repeating the self-play training process over and over again for millions of trials. This neural net ends up playing backgammon at the level of a human world champion. So it's exactly the same approach, and it's actually the exact same code that we used in Jeopardy. Now we're going to train the neural net to predict the chance that Watson is going to win from any given intermediate Jeopardy state. Okay. So once we've trained up that neural net, and it's a good estimator of Watson's chance to win, this is how we calculate the optimal daily double bet. You multiply Watson's confidence that it's going to get it right times the neural net estimate of when your score increases by your bet, plus the probability of getting it wrong times the neural net estimate when your score decreases by the bet. You do that calculation for every bet and pick the bet that gives you the highest expected chance to win. So I have a video clip that's going to illustrate this daily double algorithm in action in one of our early sparring games. And what was going on in the sparring game, we started playing Double Jeopardy. Watson had a big lead, and it started running the first column. It got the first 3 right, and then it hit the daily double. So for humans, if you have a very, very big lead over your opponents, you might think, well, I've got a big lead, I don't want to risk it. So you very often see people playing it safe. However, for Watson, the calculation says it's gotten 3 right in this category, so its confidence estimate is going to be very, very high, and you're going to see a very different approach to wagering in this clip.
The Russian ballerina's London home, Ivy
Double.
House, was famous for its ornamental lake with swans. Watson?
Who is Anna Pavlova?
Good for 1600. You're very good in the pronunciations today. Choose again.
Ballet dancers for 1200.
Answer is daily double. All right, you have quite a large lead over our 2 human players. How much would you like to wager?
I'll wager $6,700.
Well, all right then, $6,700. Here's your clue. He was born in Kiev around 1889 to parents who were celebrated dancers from Poland.
Who is Vaslav Nijinsky?
That is correct. Very nicely done. That brings your score up to $17,700. Our human players are still at the 4,200 mark. Choose again, Watson.
So here's a peek into the analysis that we did to come up with that wager. So the green curve is probability of winning if he gets it right. The red curve is the probability of winning if he gets it wrong. And now the calculation does a confidence-weighted blend of the green curve and the red curve. And we can see what that looks like for various different levels of confidence, ranging from 45%, which would be very, very low confidence, and it would want to bet nothing. As the confidence increases, you could see the bet go up, go up, go up, go up. Finally, if we got all the way up to 85%, the algorithm would bet true daily double. So this gives you a little bit of an insight into what factors influence the right wager, and it's completely dominated by confidence. Confidence makes the difference between betting nothing and betting everything and whatever intermediate value in between. Okay, so before we had this neural net daily double wagering algorithm, we had a simple heuristic algorithm that would use appropriate logic given the state of the game and the current scores, but it crucially did not take confidence into account. So that was a big weakness. So when we replaced that heuristic algorithm by our neural net daily double betting algorithm, we got a very substantial pop in performance. The heuristic algorithm, we were winning about 61% against humans in simulation. Plug in the neural net, and that pops up to 67%, which is quite a big improvement given that you only use this method maybe once or twice per an entire game. So that's quite a nice improvement. Okay, so Final Jeopardy, I don't want to say a lot. Basically, we do a best response type calculation. It's a game theoretic concept known from game theory, and we approximate it with lots and lots of simulated draws from a model. We developed a stochastic probability distribution of what are human bets likely to be in various Final Jeopardy type scenarios. So for any given scenario, for any given current state of Final Jeopardy, we're going to draw about 10,000 samples of the human bet pairs, and then for each of those samples, we're going to calculate for each legal bet that Watson could make which bet gives the highest payoff given Watson's probability of getting it right and wrong, and also given the human probabilities of getting it right and wrong. So bottom line, I don't have a lot of time to talk about it. You can read details in the paper. But bottom line, this boosts our win rate by 3 more percentage points than if we just used a simple-minded Final Jeopardy heuristic. Okay, so the final point is the buzz threshold. The buzz threshold is very intricate mathematical algorithm. We don't have time to go into the algorithm details, but I just wanted to give you an illustration of the results that come out of a calculation where here we've got a sample near the end of the game state where there's one clue left. The clue is worth $2,000. We're going to fix the human scores at 13,000 and 6,600, and we're going to look at a wide variety of scores that Watson might have, ranging from 5,000 when Watson is in third place, ranging all the way up to 30,000, where he's virtually assured of a guaranteed win in the game. And what you can see is that the optimal buzz threshold really does vary quite dramatically for quite intricate reasons that I don't really have time to explain what all is going on. It has to do with various different kind of Final Jeopardy scenarios, positioning yourself for Final Jeopardy. There's a lot that goes into that. And so you can read the paper for details on this, but the point is you can't just use a simple average threshold. You really, if you want to get the best possible result in the game, you really need to calibrate your buzz threshold according to the specific scenario that you're facing near the end of the game. Okay, so to wrap up, summary is this is the first ever quantitative, principled, and comprehensive approach to Jeopardy strategy, taking into account all aspects of strategy decisions. We believe we've done a lot of analysis that can document that our strategies for Watson do better than what humans are capable of doing in their strategy decision making. For Final Jeopardy, we think we have a slight edge over good players who've studied the theory. Now, if they haven't studied the theory, then we have a very large edge. But let's say we're playing against good players, we've got a slight edge. For daily doubles, we've just got a clear edge. There's no way that humans can compute these kind of wagers the way that we do. For clue selection, we get a moderate edge due to this Bayesian daily double seeking is more precise. Humans can seek for daily doubles, but not as precisely as Watson can. And finally, for the endgame buzzing, we get a clear edge in very, very special case situations where humans may not realize that something unusual is going on. And so the superhuman strategy turned out to be a significant factor in Watson's overall competitive record. And I'll just flash some references for further reading. Thanks.